Thank you very much. It's a pleasure being here. So the outline of the talk is the following. So I'm just going to start by giving everyone an introduction to machine learning and what deep learning is. And I'm going to highlight some recent revolutions that have happened within the domain of machine learning pertaining to natural language processing and computer vision and generative models. Then I'm going to share with you sort of my perspective on what music is and how music has developed through the centuries to get to where we are today. And thirdly, I'm going to explain a little bit how there is a really convenient mathematical framework that allows us to understand how all these different tasks can be solved using the framework of deep learning. And then finally, I'm going to show you some cool examples of what our autonomous DJ can do. So what is machine learning? So machine learning pursues the idea of creating AI by building algorithms that can learn from observed data and generalize to unseen data. So when we try to accomplish this generalization, we have to look into things like whether we have a data set that represents what we want to understand. And if we don't, we can anticipate sampling errors. And we also want to understand whether we can make well-conditioned algorithms that can find the models that we frame as solutions to our problems. And if we can't do that, we have optimization errors. And we also want to know whether our model that we come up with is well-conditioned to represent reality. And if we don't, we have an estimation error. And all these errors can accumulate to make up something called the generalization error. So the one takeaway is that machine learning is all about being able to answer questions about data that we've never seen before. But to get there first, we train the models on data that we collect. So doing this, we can solve new types of problems that we cannot solve with heuristical approaches. So we can describe the types of problems that don't have a quantitative descriptions or may even have solutions that are very subjective. So for instance, if we want to create good music with AI, whether the music is good or not is very subjective. And for example, the task that most of you can perform, which is to recognize your partner by smell, for instance, that's a task that is very difficult to quantitatively explain. Your brains just sort of know how to do it. And those are the kinds of tasks that machine learning algorithms can also solve. And deep learning is really just machine learning using deep neural networks, which is a device for efficiently learning hierarchies of representations. So that means that, for example, if I look at an image, I can recognize, if I look at an image of a car, I can recognize the car by the different wheels and by very many different features that the car is made up of. And neural networks can automatically understand how these different features combine to make up the concept of a car. So if we look at what has been happening in computer vision for the last few years, we would see that these deep neural networks are everywhere. So the reason for which is that these networks can be trained to solve these tasks very efficiently when they are run on a graphics processing unit or a GPU. And so we can solve different types of tasks, such as classifying the image itself or classifying the different pixels of the image. We can also solve the problem of pose estimation, which is to judge which pose a given person or an object is in. And we can also make models that so we can make models that can generate data from nothing. Yeah, on the YouTube, thank you. So you see the source A here are the different attributes that each of these images are tuned to be like, and then we choose another image here, and we try to make what is in A as close to B while maintaining these attributes here. So this is something that is very interesting, because now we have an algorithm that can create these human faces, even though these humans have never existed ever before. So that's an example of something that generative models can do. We can also solve problems in natural language processing, such as translating one language into another, or understanding the sentiment of a sentence, or even do syntactic tasks, such as spell checking. And recently there has really been a revolution in doing natural language processing because of this model that is depicted here, called the transformer network. And these models can do something that previous language models could not do, which is that they can learn from large corpuses of text and then later be fine-tuned to specific applications that may have very small data sets. And the basic essential trick behind making this architecture work is to try to make the computational flow that relates one word to any other in the sentence be as short as possible. So I wanted to sort of highlight some recent theoretical developments that have that I'm really interested about. So one recent theoretical development is in choosing how to make your neural network architecture. So there's an operation called batch normalization that was discovered in 2015, and it basically normalizes your data to have a given mean and according to the mean and the standard deviation of a sample batch. And although this has increased performance of algorithms in the past, it seems that there are many problems with this operation. And I would just like to mention that Angus here, who introduced me to this particular paper, he's in the audience, and he just published a paper at NIPS that goes further into thinking about this problem and relating it to a concept known as adversarial examples. So there are also very interesting mysteries surrounding the fact that the neural networks work so well. And there are recent papers in the mathematical literature that claim that these neural networks are finding the global minima of the objective function, which is surprising because the objective function is not convex. And another recent discovery that is very interesting is that there is a way of maximizing a quantity known as the mutual information that allows us to train neural networks on large data sets that don't have any annotated labels. So one problem with making these algorithms work is that often we need an army of humans to label the images or the examples in the data set. And there's this recent paper called Deep Infomax that shows that you can actually take a large data set of data that has never been annotated before and train the network on that data, and then apply it to a smaller data set that actually has labels. And this is something that has remained a really big challenge in the community, but is something that has been solved recently. And so I just wanted to sort of highlight to you the vibe of being in this research area and how we are, as a community, we are always solving these challenges that seem very difficult, but as a community we get there, and machine learning is going to become even greater in the next few years. I can convince you of that. So just to step down a bit, I wanted to explain to you how this can have anything to do with music. So one of the most interesting things to me about how machine learning and deep learning works is that we have a rather simple framework for solving very different problems. So the question that we are asking us at Rave is whether we can leverage all these findings to make AI create music the way humans do. And so let's start by thinking a little bit about what music is. So as a mathematician, the one thing that is very important to us is how we can represent the music for the neural network. And what we do is we use this famous transformation called the Fourier Transform. So this picture is taken from this excellent book by Jan Stewart, 17 Equations That Changed the World. So what we see here, so the function f of x is the waveform. So it describes the sound as it changes in time. So x is like time. And so the sound is just a wave that has different amplitudes at different points in time. And then if we apply this transformation that takes the integral over the entire domain and multiplies by this exponential function here, we can transform from the space of amplitudes per time step into the space of frequencies per time. And so to just show you what this looks like, I wanted to show you what this looks like when you apply it to music with instruments and without instruments. So this is one of my So what you can see here, so these are low frequencies here, and then we have higher frequencies as we go up. And it becomes black when there is silence. We can see here the different harmonics in David Bowie's voice. And this way you can sort of make the audio into an image that you can later feed into the network. And so this is absolutely instrumental for being able to leverage advances in computer vision for audio. And so we can see what this looks like if we take a look at it in its original version. So you can still see David Bowie's voice in here, but now you have the bass underneath going, and you have these different tonalities that appear in the spectrogram. So this mathematical description that is really instrumental for making this work is actually a description that goes all the way back to the work of Joseph Fourier in the 18th century. And he used it to be able to solve an equation called the heat equation. So you can use this same technique to solve very difficult mathematical equations, and then when we apply it to sound or any wave that we can think of, we can make these beautiful images that give us good descriptions of what is going on. So turns out that this is actually very similar to how humans process sound. So the sound goes through the ear, and there's a membrane in the ear that vibrates as the sound waves come through it, which makes these tiny bones here, the malleus, the incus, and the stapes, bang on this drum here. So this snail-like structure called the cochlea contains liquid, and as these bones hit this structure here, there are ripples that get created in the liquid inside it. And as these get created, these tiny hairs that sit on this brain membrane vibrate. This is happening inside your head right now. And as these vibrate, there are ions that get released. And these ions, they go they get released, and they go through the hair strand, and they activate these neurotransmitters that make the auditory nerve go, ah. And the auditory nerve does whatever it does, nobody knows, and takes these signals and brings it to the brain. And what is interesting is that just as with the Fourier transform, we have the low pitch part of the spectrogram here associated with these hair fibers down here, but we have higher pitch ones at the top, at the apex of the cochlea. And so your brain actually decomposes the different frequencies in a very similar way to how the Fourier transform works. And that's how we process sound. And so we process sound, but music is this cultural activity that has been evolving throughout the ages. And I just want to share sort of my perspective, how I put all of that in context with what we are doing at Rave. So if we just think about music from the 18th century, we have Johann Sebastian Bach making these fugues. He is using an organ, a really large instrument that cannot fit into a household very easily. And it's an instrument that relies on air going through pipes. So it's really difficult to get anything dynamic out of this instrument. It's just you press one key or the other. So this is kind of a good description of how an organ works, because it's sort of binary. So when you make these kinds of fugues, so when you make fugues, the idea is that you have these different melodies going on and trying to mimic or reflect on one another. And Johann Sebastian Bach is sort of thought to be the genius of the fugues. He sort of came up with this way of making music and wrote about it and inspired many classical composers. So after Johann Sebastian Bach died, the organ sort of lost some of its popularity, and people started thinking about pianoforte, which is what people call the piano, soft and strong, so you can actually create this dynamic sound that you want to listen to, and people love so much. And so this is one of my favorite composers, Chopin. So one really interesting thing about living in this time, in the 19th century, is that people didn't have radios. And when people want to listen to music that had just been released, what they would do is they would get the sheet music, and they would find someone in the household who knew how to play the piano, and then they would sit and listen to whoever was able to play the piano. So as these new instruments got created, the music changed according to that. So what was music like in the 20th century? And I just choose this because this is one of my favorite bands. But to me, music in the 20th century is about making music with electricity. So these guys, this is the biggest band in North America in 1970s. And these guys, 19 years old, and you can see how people made TV back in the 70s as well. It's very spastic. And this was actually the most popular music in North America. And it's just these guys going nuts with electricity. So they have the guitar, and they're not doing anything complicated. They're not using pedals or effects or anything like that. They just have a really big Marshall amp, and they put the volume way up so you could hear the gain. And then they had this really, really talented vocalist who was able to scream his lungs out. Yeah, so this band is really awesome. So this song on the CD this song is like 7 or 8 minutes or something like that on the CD. And whenever they would perform this song at concerts, they would perform it for like 20 or 25 minutes. They would just like not stop playing it. So that's how music used to be like in the 70s. So what is music like in the 21st century? So music in the 21st century is all about composite art in many ways. So Kanye West, who is also one of my favorite musicians, thanks to Colin and other people at Rave for introducing me to him. So this part of his music video is actually stolen from an Icelandic artist called Björk, who is one of my favorites as well. So Kanye West is a really, really talented producer. He is a very creative artist who just keeps on making incredible music. But he makes music totally differently from Chopin or from how Led Zeppelin made music. He takes things and he's able to digitally jump between different sections of songs and put them together in an intelligent way to make this new composition. And this is where we started at Rave in trying to understand how we could make music. So we tried to make music like Kanye West. And so this is one of our own compositions, or made by our DJ. Here. Oops. So this is a mashup of a Korean band and Taylor Swift. So the two songs are combined together into a seamless mix. So what I really like about this is that I feel like this composition, in my honest opinion, is better than the original compositions. So that makes me happy. So this is made by a click of a button on our website, rave.dj. And any of you can do the same thing with your own music. And we are tirelessly working to make the system even better and even more sophisticated. But so I want to tell you about probabilistic models, which is this really nice framework that gives you this nice layer of abstraction that allows you to think about how you can apply machine learning to many different domains. So this is the domain agnostic idea. So we can talk about probabilistic models. So there are two types of probabilistic models we can talk about. There are prescribed probabilistic models that model the parameters of the underlying distribution explicitly. So for example, a Bernoulli distribution is the distribution that tells you whether or not you get heads or tails when you flip a coin. So the parameter of that distribution is the probability of getting heads. And the sample of that distribution is heads or tails. And so if we want to make a model that predicts the probability of getting heads, then that's a prescribed probabilistic model. And there are many of these. So all these state-of-the-art classifiers for object recognition and computer vision and state-of-the-art translation models, they are prescribed probabilistic models. But for the problem that we are considering, which is music generation, we actually prefer thinking about implicit probabilistic models. Those are models that define some stochastic procedure which can generate data that is indistinguishable from the underlying data distribution. So, for example, an implicit generative model would be a model that would flip the coin again and again, and if you would look at the statistics for whether you get heads or tails, it would be indistinguishable from actually flipping the coin yourself. So the human face generation example that we saw before was another example of an implicit probabilistic model. And these models are also being investigated for drug discovery and many other applications where it's really difficult to explicitly state what you should be getting out of the model when it makes predictions. And so just to give you a little bit of a formal statement about how this can be put in the context of deep learning. So if we assume that f theta is the deep neural network, which represents a real-valued function in a vector space, and theta are the parameters, those are the weights of the neural network at any given layer that has a depth L, then we let L be a function that takes as arguments these other functions, which are the conditional functions represented by the data distribution and by our model distribution. So what we want to do in deep learning is we want to solve this kind of an optimization problem where we want to find the parameters theta that minimize this quantity L, this quantity produced by the functional L. And typically, we get the solution by just considering the steady state of this optimization process that we get as we do this iterative process of saying the parameters at time t plus 1 are the parameters at time t minus the delta that you get in the expected value of the loss. So in expectation, we should converge to a local minima. And this works so incredibly well that it's actually quite, it's very fascinating. So this is sort of like a formal statement of how we can frame neural networks within a probabilistic model. So we find the probabilistic model by solving this optimization problem. And what we really want to do to be able to solve the optimization problem is we need to be able to estimate this quantity here, which is the expectation of any given function f, which could be the loss function f. And we want to be able to find the gradient with respect to the parameters of the distribution that our probabilistic model represents. And so what we typically do is we come up with this estimator, t hat, that gives us an empirical estimate of this quantity here. Because this quantity here is an integral, we need to be able to represent it in a way that the computer can give us a number. And we say that this estimator is unbiased or well-conditioned if in expectation the estimator returns the same thing that we wanted to be estimating. So as an example, there is this reparametrization trick that was invented in 2013 and has really created this revolution of latent variable models and probabilistic models in deep learning that has led us to be able to consider these kinds of tasks. So if we have a random variable that is measured by the law of the Gaussian distribution with some parameters alpha, we might want to maximize this quantity here. And so we want to find a good estimate of the gradient with respect to alpha of this expectation. The problem, however, is that the parameter is alpha is underneath the expectation. So if we want to find the gradient with respect to alpha, we need to somehow find a way to differentiate this thing here. But we don't have access to alpha when we look inside the expectation. We only have access to the samples of this distribution Q. So there is this really awesome technique that was invented by Max Welling's lab in Amsterdam that says that you can do a change of variables or a reparametrization of these samples that you have access to and think about them in terms of an invertible differentiable function t that takes in the parameters alpha as well as a noise variable epsilon. And so using this function, we can rewrite the expectation we want to estimate. So we can take this, which we had before, and we can move this away and replace it with the noise variable, and then we can differentiate with respect to alpha by using the chain rule, by replacing z with this t of epsilon alpha. And because we don't need to differentiate through p epsilon, everything's fine. And so we get the gradient we want. And so this is an example of a discovery, mathematical discovery that was made in 2013 that has been a key finding for defining various probabilistic models. And so in the end, I just wanted to show you a few other mashups. Do you want to see more? So let me see. This one? Yeah. I want to use the opportunity also just to recognize the efforts of everyone who works at this awesome company. So there's Mike, Garrett, Colin, Armel, Andy, Ocho, Stefan, Nick, Andrew, Julia, and Matt. And just like, thank you very much for helping us make this happen. It's been, it's really great, and it's going to become even better, I'm sure. This is going to be the last one, I think. Yes, absolutely. Yes?
So a lot of pop songs are kind of written in very similar keys. Yes, of course. So a lot of pop songs are written in very similar keys. So what happens when there's mashups between songs that are written in very different keys, for example?
So what our algorithm does is that it tries to anticipate for that by pitch shifting the other song such that the keys match properly.
What will it shift to? Will it shift to, like, will there be more powerful song?
I mean, so for the key per se, we allow it to shift up to or down to 2 semitones. And so there's like a recipe that allows you to understand which keys go well together, and the DJ sort of learns to follow that recipe. Yeah. Yeah?
First, I just gotta say it's really cool what you built.
Thanks.
So, forgive me because I'm kind of neophyte, but you said there's like implicit probabilism to like try to build what might actually be in the data. How far away are you from actually creating like a song from scratch?
I don't know. It's a good question. So there is, so one can look at the research in computer vision to try to understand how far away we are. So the human faces that we saw before, they are created by conditioning on attributes. So you know, the model knows beforehand which attributes you want to be preserved with the image. And those kinds of models, they can actually do really well for specific type of data, like human faces. It's not a very varied data set. So as the complexity of the data increases, it becomes more difficult to make these kinds of unconditional algorithms work that don't depend on very much structure to understand what they should be generating. And research on that seems to indicate that there's something just really difficult about that problem. So the state-of-the-art probabilistic model in doing unconditional image generation is actually a prescribed probabilistic model, but not an implicit probabilistic model. Yes?
Sorry, second question. I'm monopolizing time. Have you tried doing that or spoken word?
No, but that would be really interesting as well. But then you would have to think a bit about what people are doing in speech processing. And so it seems like when people do speech processing, they have to be more careful about how they choose their input domain. So I didn't really talk about it, but the Fourier transform is at the basis of how we create these input domains for audio, but there are many different ways of going about it. You can, for example, take the Fourier transform and then take the logarithm of the output and then take the Fourier transform again to get something that people have found very useful for understanding spoken words. But it's definitely something that would be really interesting, especially for music like hip hop, where what people are saying actually kind of matters. Yeah. Yes.
What about mixing in some like classical music with like the Britney?
That would be super cool. I don't know.
Are we able to try that on your website?
Yeah, you could totally try that. Yeah, you can try anything. That's kind of what we see this as being. This is sort of a tool that is not replacing DJs, but it enables people to make music in a totally different way. Just like the piano enabled people that would have otherwise played the organ make music in a different way. And how being able to manipulate tracks digitally made producers able to make music in a totally different way from how Led Zeppelin make music. So you have access to this tool that interprets and manipulates these outputs of the Fourier transform automatically for you, and you just have to give it the songs you want to try to mash.
Follow-up question. On that slide where it showed all the people working in your office, what percentage of those were real photos and what percentage
were I'm not sure. Yeah, I'm not sure whether Nick exists or not after seeing what happened to him the other day when he face-palmed the street when biking. So we'll see. Maybe he's a robot or something. Yes.
So going back to your definition of
Yes.
And the examples that you've given are kind of a very prescribed type of mashup.
Yeah.
I'm wondering what it sounds like when it fucks up, when it fails to your definition of what you want to hear.
Yeah.
What does that sound like?
So sometimes people put songs together that don't go very well together just because of the key. Like you were pointing out would be something that you might want to know about. And so sometimes, because we don't yet have the ability to pitch shift the instruments without pitch shifting the vocals. And so when we have to pitch shift the vocals of one song a lot, and it's like a very famous singer, it sounds really bad because you just yeah, but I don't know, with it, do you want to pitch shift Ariana Grande's voice up by 2 semitones? Then she sounds kind of like a squirrel or something. It's kind of, I mean, to me, that's one example of something that can go bad. Another example is just when the time signature of the songs are very different, and that's something that we're working hard on trying to be better at. But when the time signature is not 4x4, then we usually get really bad mashups. Also, when for some reason it's difficult to detect where the drops are in the songs, then things can go really badly just because you're piecing together something that doesn't really go together. Yes?
So what's next for Ring?
Making better music, making more interesting music. We are currently trying to make a better way for our users to take authorship of their mashups by having a sort of like a social network through rave.dj. So you can register as DJ Bob or whatever your DJ name would be, and you can sort of make your mashups and share them with other people, and so other people will see, aha, DJ Bob, he's my favorite DJ. And this is sort of like a problem that we've had, or we wouldn't call it a problem, but our website has grown organically for the past couple of years. And what we're seeing is that a lot of people download mashups and put them on YouTube. So if you just go on YouTube and search Rave DJ, you will see mashups being uploaded like every 5 minutes by people from our user base. And I just like, because we're talking about our users, I would just like to point at Garrett, who is the CTO of our company and has made this incredible system a possibility. So our website, due to Garrett and his team's effort, is able to process around 10 terabytes of data per day. And so we really believe that as we get better and the website becomes bigger, we can really make history in terms of enabling people to make interesting musical compositions. I think we already are to some extent. Yeah.
Can you mash up more than 2 songs?
Not at the moment. That's also one thing we're trying to work on hard. So the machine learning team is really, we also have mixes where you can put together multiple songs, but at the moment we're just trying to identify the best way of transitioning through the songs. So you can take a playlist from YouTube or Spotify and make it into a mix and listen to it. Yeah, so it like seamlessly transitions between tracks. But to make it even more interesting, we would like to inject mashups into the mix so that we can really surpass what a human DJ can do. Because also we are manipulating, we also have the videos, right? So that's something that takes a ton of work for a human DJ to make possible. Yeah, sure. You could totally do that. That's the naive. That's what the engineer does. The mathematician tries to find an elegant approach, but yeah, you could do that. Yeah.
Last question.
Oh, okay. From a marketing standpoint, are you guys currently working with any world-renowned DJs?
No, but that's one thing we'd like to do. We'd really like to get in touch with good musicians, because we really see ourselves also as musicians, kind of a strange band, but yeah. So yeah, I really want to contact the Antwoord and have them work with us. We will see.
So, one more, like,
Yeah.
how do you
Oh, that's a really good question.
Okay, if you could put your hands together.